Okay, good afternoon. And first of all, I really appreciate the opportunity of being able to come over to Helsinki and talk about a few of my passions, Windows Azure, driving games, physics, and Formula One. So the session I'm going to be rounding off with is really talking about a pet project of mine, which has kind of been a hobby project, which has been consuming a lot of my time since about October last year. But there is a really serious side to this, because with the development of Windows Azure and cloud computing and the emergence of technologies, things like the Internet of Things, connected devices, all this type of telemetry stuff, the stuff that I'm looking at and developing when I'm building this game is really useful techniques that we can use in the industry. And my prediction is that there is going to be a really big growth in this type of technology, these types of projects working with telemetry data. So I'm really sort of aiming to develop some ideas and share some ideas about sort of my opinions for how this technology is going to be used into the future. So one of the things that got me started in this project was hearing about the development of Xbox and how the games, instead of just being a game console that you ran on your PC at home and played on your own, games are now becoming a lot more networked. So since I've got an Xbox 360 at home, we've got Xbox Live, we can connect to that and we can do multiplayer games. The Xbox One is focusing a massive amount of energy in developing its live services. And this is a news report that came out last year talking about the new services that are going to be powering Xbox Live on Xbox One. 300,000 servers for powering the games and game DVD. And this back end is really built on Windows Azure technologies. They're using the Windows Azure Service Bus for Halo. They're using Windows Azure Storage for storing lots and lots of game data. So using the cloud platforms for building these backends is something that not only Microsoft is doing, many other game developers. Think about how many mobile game developers there are, developing mobile games. Think about the challenges that most of those are small companies. They don't have infrastructure to provision. They want to be able to have the potential to support millions of players playing online games and do this as cost effectively as possible. They want very rapid scale. When you look at cloud computing, you're fairly used to the usage patterns, the typical usage patterns of cloud computing. Running a website for the Olympics, for example, you've got massive demand over a few weeks and then very little demand before and after the event. For any kind of a gaming company or companies like Twitter, rapid growth is important. You want to be able to scale to meet the demand of your users. And you can see from the graph, towards the end of 2009, 2010, Twitter were just really fighting. They were basically firefighting, trying to scale up their environments to be able to handle the demand that's coming onto those environments. You've also got something like predictable burst. You can predict the load capacity on Formula1.com for the rest of this year. We know when the Grand Prix are going to be. We know when that site is going to be busy, pretty much down to the hour and to what actual percentage capacity we're going to be requiring. It does require scalability. We don't want to be running the full production environment through the winter season. We maybe, when they take that long break in August, we don't want to be running the full production environment then. But we do want to be able to providing a very good user experience to the users when that site is popular at the race weekends. We've also got unpredictable burst, and this is the classic example there that I take is the news sites. We could have a global news event that's happening in 2 or 3 minutes' time. With people using Twitter, Facebook, email to share information about what's going on in the news, instead of it being a few hours before somebody actually goes on the internet and sees the latest news story, it is going to be seconds and minutes before people are going to be logging on to actually catch up on one of these news events. So these actual production environments that are hosting the news sites, they need to be able to scale in seconds and minutes. And it's a challenge that the capacity on a news site could need to double in 2 or 3 minutes' time, and they don't know when that's going to happen. It could happen tomorrow, could happen in 5 minutes' time. With the actual games industry, with the games that are being launched on the Xbox One and Xbox 360, they kind of have a different usage capacity graph. They have something which is known as launch week. So when Halo 4 was launched, they had massive demand on that game. It's very, very popular for the sort of first week during the actual game release. And then the actual demand trails off. It gets less and less and less. So in 6 months or 2 years' time, There's a few die-hard fans who are still playing that particular game because they have a group of friends who play that particular game. But most people have moved on to playing other games. The game needs to work on launch week. Having a failure during launch week is a complete disaster. They don't have any time to prepare for that. Testing for that is very, very challenging. And a failure during launch week is going to cause lots of issues for the actual gaming company. And I kind of think computer gamers are the angriest people in the world when things go wrong. You know, you do have customers that you deal with, but the gamers, they will start yelling and screaming if anything breaks in that gaming environment. So a bit about how Halo is using Windows Azure. We have various Xbox Live services. These are the core services that all games will have. Things like membership, leaderboards, downloadable content and achievements. That's all part of Xbox Live. But Halo and many other games are really wanting to go beyond those core services. So they're providing mobile apps, Windows 8 apps, Windows Phone apps like Halo Waypoint, where you can see where your friends are, you can see how people are playing the game, you can see people's game presence. So Halo is making extensive use of services in Windows Azure, like the Windows Azure Service Bus, to be able to drive the game statistics, the game presence, where you are in the game, things like the multiplayer game stats, and also cheating and banning. So based on the way that other people relate to you in the Halo game, they're able to actually auto-ban people if they detect or they think that they're behaving inappropriately during that game. So if you do want to get a bit more experience on how Halo is using the service bus in Windows Azure, there's a couple of great resources. The first one is on Channel 9. It's Clemens Vastas and Hoop Samoa and a few of the other actual Halo team talking about some of the challenges they had actually putting Halo onto the service bus. If you ever listen to the Hansel Minutes podcast from Scott Hanselman, he's actually speaking to Katie McCaffrey, who's again giving a really detailed description of how Halo is using the service bus and some of the challenges that they have with the service bus. Another of my passions, Formula 1 and telemetry. I'm also talking about telemetry, device telemetry here, and game telemetry. Formula 1 is probably the industry that has taken the lead with working with telemetry-based systems. They've had millions of dollars of budget to invest in various systems, and what they're really interested in is getting the information from the car to the track side, so they can actually make diagnosis on what's going to be happening. You're watching a Formula 1 race, and suddenly a radio call goes out telling somebody to actually abandon the race. And this is because they're actually detecting problems in the engine, like the engine is overheating, there's low oil pressure, and they need to bring that car in. When looking at the way that the telemetry data works, this is basically the engine control unit that we've got from a Formula 1 car. The ECU, or the engine control unit, they're all made by McLaren Electronics, and that was a partnership with Microsoft several years ago to actually develop these types of systems. We've also got telemetry. This is courtesy of Lewis Hamilton on Twitter, if you remember this story a couple of years ago, basically showing how the cars are performing. We've got all of the different statistical information coming from the actual device there. So the telemetry data is sent there out to the actual systems that are picking this up, and it's used in a number of ways to actually sort of diagnose problems of the car, provide feedback to the drivers and so on. When I started watching Formula 1 in the 70s, it was cigarette companies that were sponsoring the Formula 1 teams. Now, most Formula 1 teams will have a technical sponsorship. The Renault team is sponsored by Avanade and Microsoft Dynamics. When I was at the MVP Summit last year, I bought this Renault racing shirt in the Microsoft store. They had all kinds of Renault merchandise because of this partnership that's going on. It's not just about having the Microsoft logo on the car. There is a technical partnership between the Microsoft company and Avanade and Renault to actually help with actually building and getting all of these systems in place and working.
I work on a very important project for them, which is called PEP, Performance Engineering Program. And the purpose is to build this tool with them this year and prepare for the next season. After only 3 weeks, I find this very exciting because I work with 5 other guys. Also, we work with race engineers, performance engineers, so the guys who go on the track side. It's very exciting and very challenging.
As you'd expect as a Formula 1 team, our major focus is on the track in a performance domain, optimising the way the car performs. Probably the best example is to do with reprocessing of post-event data, where we've seen a 75% reduction in processing time, which is a seismic shift really for our engineering staff.
So what they're talking about there is how they're sort of managing and processing this telemetry data. It was a promotional clip from a company called Avanade. If you don't know that much about Avanade, they work very, very closely with Microsoft on the Microsoft technologies. So you can put two and two together and figure out that Microsoft technologies that are used in these particular scenarios. So there are a lot of challenges with Formula One racing where cloud computing is going to be very useful. They do the practices on Friday. They generate tons of telemetry data that needs to be analysed by Saturday lunchtime when they're going to be doing the qualifying. So having on-demand systems that can process this data is very, very useful. They're also located in different locations around the world, so having communication over the internet with different systems is going to be critical as well to those organisations. Another reason where we hear the words telemetry mentioned, and we hear lots of talks about telemetry, is the Internet of Things. Just reading the news articles on this, Coca-Cola purchasing 16 million network IDs, because all of the machines, all of the soda dispenser machines that Coca-Cola are going to be generating are going to have networks. They're going to be connected to the network. So every time somebody buys a Coke or buys a Fanta or gets a drink out of this machine, data is recorded and data is sent into systems. So the Coca-Cola service engineers will know, looking at all of these machines, how many drinks each machine has dispensed. And after a certain number of drinks, the machines need to get serviced. The machines will also be able to report problems. If the machine is malfunctioning or needs cleaning, it will be able to send notification messages out to other systems. Google purchased Nest, a smart thermostat company, for $3.2 billion. Home automation is also something where telemetry and Internet of Things, connected devices in the cloud, I predict is going to be a very big business. Being able to actually control thermostats, these home automation systems. So what is the Internet of Things? I'm going to mention this briefly. I won't spend too much time talking about it. It's basically devices that can be connected to the Internet, and very often, for scalability and connectivity reasons, we're using cloud-based systems to be able to actually manage those integrations there. So we're developing systems on these cloud-based platforms that can integrate with those various devices. How do you get into it if you're a hobby developer? There's a picture on the screen, but I've also brought this thing along with me. This is basically a pie brick, or a brick pie. It's made by a company, a robotics company, and it's based on the Raspberry Pi. So there's two boards in here. The bottom one is a Raspberry Pi. Costs about 20-25 euro to purchase a Raspberry Pi. It runs Linux. It's got a network adapter there. Doesn't have a hard drive, but it's got an SSD drive there, and you can actually integrate this with Windows Azure Service using HTTP requests out to the Windows Azure storage services. You can download a library that can integrate this with a Windows Azure Service Bus, so these devices can basically be connected to Windows Azure. I've also got Lego Mindstorms components hanging off this, so you can plug in motors, you can plug in sensors, you can get telemetry data, you can send commands, and we're actually working on a project in-house at my company to develop it's just basically pet projects that we can do. So on Wednesday afternoon, we're basically looking at building a robot that's going to be controlled through Windows Azure in a secure way from a website, and is going to be able to send back a telemetry data and stuff. So it is, open and very accessible for the hobby developer. Also, very cost-effective, paying 20 euros for a device that you can integrate with the internet and be able to actually put that device in a fleet of delivery vans or a fleet of taxis or coffee machines, soda machines, photocopiers, all that kind of thing. There's going to be a real growth for potential in that industry. So this is our coffee machine at work. You've probably heard how the Swedish are passionate or obsessive about coffee. I'm coming from England. I tend to see that. So we have two weighing scales on the coffee machines. We have a Raspberry Pi that's sending messages up to the Windows Azure Service Bus. So we can actually see the actual weight of the coffee in the coffee machines and know when the coffee machine needs to be changed and so on. So it's kind of an amateur thing that we're doing, but for being able to actually send out service engineers to the correct coffee machine, if you've got 10,000 coffee machines at 10,000 different customer locations, that's going to be very good for the companies who are manufacturing these things. As I've said, this hobby development is leading towards really useful scenarios in industry. Scenarios where this could be useful, for example, power cuts in America because of the infrastructure that we've got. When it gets very hot, everybody turns on the air conditioning, and that is basically causing outages and so on. Be able to integrate the devices with the cloud will allow electricity companies to be able to actually, prevent these types of events from happening. It's much better to turn everybody's air conditioning down by 10% than it is to actually lose power in a neighbourhood and everybody loses electricity in that neighbourhood. So that's some of these scenarios that people are looking at. So a bit about the information exchange patterns. Telemetry, I talk about this a lot. This is a device sending information into a cloud-based system or an actual system. So in the when thinking about an air conditioning unit, it's going to be sending the temperature, it's going to be sending the power, the various settings going up to the cloud. Inquiries, the actual air conditioning system may send out a request for the actual weather. Is it going to be cold tonight? Is it going to be warm tonight? Do I need to actually think about cooling down the house? Or is it going to get cold anyway in the evening and I don't need to do that? Obviously, commands from mobile devices, we should be able to turn our devices on and off. We should have that home automation. So sending commands is also another pattern. Notifications, we could also choose to notify the devices of the latest weather. This information is broadcast to all the devices every day to let them know what the current weather forecast is going to be. So a bit about this game that I'm working on, which I've titled Red Dog Racing. From Formula 1 we have Red Bull Racing, the Formula 1 team, and the code name for Windows Azure was originally Red Dog, and I kind of decided on Red Dog Racing being the name. The reason I'm building it, I'm really passionate about Windows Azure. I'm a Windows Azure MVP, Windows Azure Insider. I deliver Windows Azure training courses. I run a Windows Azure user group. We've also been running the Cloudburst conference in Stockholm and the Global Windows Azure Bootcamp. So my head's in the cloud, really. I'm always focusing on scenarios where customers can be working with Windows Azure in their projects. I was a physics geek at school, so this kind of stuff I found really, really interesting. What happens when a car jumps off a ramp? How fast is it going? What's the air friction going to be? What angle is it travelling at? How much does the car weigh? Where is that car going to land? And this is kind of like, I had this kind of natural ability to be able to figure this stuff out at school and do really, really well in these types of questions. And when you're building games, I do have a session where I talk about physics in driving games that I've delivered to some user groups, and I'm delivering at another conference. And it's just fun to talk about this stuff. It's fun to play around with that stuff in 3D games. I'm also a Formula 1 fan, so I understand a lot about how telemetry works, why people use telemetry, a lot about what information is relevant to get back to the driver. So I'm really interested in sort of the technical reasons for using telemetry and using these systems. I also like playing driving games, so I sit up at night playing Forza Horizon is the one that I'm playing at the moment on the Xbox. I kind of like the way the physics works in those games. I really appreciate the work that goes into producing one of these AAA rated games, and it's great to see that type of development going on. So a bit about Red Dog Racing. There was a gaming platform that you may have seen which was called XNA. Microsoft released it a number of years ago to allow hobby developers to release games for the Windows desktop and the Xbox 360. Unfortunately, XNA has now been deprecated, but there is a community project that's picked up this technology, which is called Monogame. Monogame also supports development for Windows and Windows 8, and also the iPhone devices and Android devices. So it's really a cross-platform way of being able to develop games using Mono, but still using the actual infrastructure that we've got, all of the actual classes and the base technology that was used in the XNA platform. So that's an open source project. We've also got Unity, which is another game development framework, which is very popular as well for cross-platform development. So I'm using XNA, but Monogame and Unity can also be integrated with Windows Azure, using pretty much the same technologies that I'm doing. So I really wanted the game to be an example of how we can use Windows Azure in gaming technologies, and also for the Internet of Things, and for these types of telemetry, large scalable, large device scenarios. So I built these various integration points and basically interface the game with Windows Azure. When I was designing the system, this basically is something that you will have in common when you're building any Windows Azure application. I started learning Windows Azure in 2008 and 2009, and in those days, Windows Azure consisted of a few basic services. We had Azure Storage, we had Windows Azure websites and web roles, we had the Windows Azure Service Bus, and we didn't really have that many more technologies. Now, Windows Azure has been evolving rapidly. We've got big data with Hadoop, we've got Windows Azure SQL database, we've got traffic managers, media services, content delivery network, identity management, caching, and all this type of stuff. Being an Azure MVP, I get a lot of information, and we talk a lot about the Windows Azure technologies. And, you know, we're really struggling. It is a full-time job for us to actually keep up with everything that is evolving on this platform. But today, Windows Azure consists of a large number of different services. It's kind of like .NET. You know, there's all kinds of stuff in the .NET platform. We're building an application. Do we build it in, you know, WPF, or do we use some web-based technology, or do we use a Windows Phone app or a Windows 8 app, or a combination of each? How do we handle our data storage? Do we use Entity Framework? With Windows Azure, it's the same questions. We've got this sort of big choice of different technologies that we can use, different services. So if we're going to be building an application, we may choose to use storage or SQL database. We may choose to use caching to reduce the load on our database, but maybe media services and networking and messaging just isn't important to us. So choosing and selecting the right services and composing an application, to me, is one of the sort of main things we're going to be doing in the initial stages of Windows Azure projects. So it's good to have a good understanding of how those basic services work. So I do have some of these information exchange patterns. When I was working with a driving game, I wanted it to be something fun to work with, but I also wanted it to relate to the Internet of Things. So the game will send telemetry data to Windows Azure using the Windows Azure Service Bus. It sends details of the drivers, it sends details of the sector times, it sends details of the lap times. It basically samples all of the driver data 5 times a second or 10 times a second, and sends a message a second onto the service bus. So you can get really detailed information about how the drivers have been driving the laps. Sector times, it sends all the different details of when you pass particular sectors on the lap, so we can see who's in the lead, who's in second place as well. I send various parameters from the physics engine as well. You know, where is the car in the game? How fast is it travelling? What are the actual forces on the car? What is the downforce, the centrifugal force? So we can actually, I haven't done this yet, but play around and analyse the telemetry data to figure how well a particular driver is driving around a lap. Why is one person better at going around a lap than another person? Do they brake earlier? And so on. Inquiries. When the game starts up, it makes a request to a REST service which is hosted in a Windows Azure website, and it gets back the actual lap timing data for all the other drivers who've driven the lap. So when you start the game, you'll see everybody else's lap time appearing in the actual game. When you're racing the game, it's not a multiplayer game in that you're going to be competing against other players in real time on the actual map. But when you complete a lap, your replay data is saved into Blob Storage in Windows Azure. And the game will basically download ghost cars for the top players. So when you're actually racing, you're racing the ghost cars from other players who've actually completed that lap. And every time you overtake a ghost car, you'll basically move up 1 times in the actual rankings for that lap. Many other games that you play will use exactly the same technology. So you'll have this ghost car feature where you can, compete against your friends and compete against other players. And Windows Azure provides a very scalable way of being able to provide that implementation. Commands. We've also got the option to be able to send commands down to the game. I kind of didn't have a natural implementation for this, so I actually do workshops where people can, actually run through labs and integrate the game with Windows Azure. And one of the challenges of the labs is, you've got to get the game integrated with Windows Azure Storage, and then you can drive a lap at the end and you'll see your data being dropped into Windows Azure Storage. However, because the developers have access to the source code of the game, they can reduce the mass of the car, they can increase the power of the engine. So what I've actually put into the implementation of the back-end code is we have some kind of a race control. So I'm monitoring the telemetry data that's coming in, and if the cloud-based application thinks the car is going faster than it should be going, then we've got an actual punishment message that we can send out to the driver. And it's kind of a way of being able to actually send some kind of a control message out, and hopefully in the demo I will show you how that actual punishment method works, because it's quite interesting. Notifications. When another player sets a lap in the game, it will basically send out a notification on the Windows Azure Service Bus, and you will see messages popping up on the screen saying so-and-so got a particular time in this particular lap. I'm going to work on the implementation of this. I'm not currently doing it in a very scalable way. I would like that to be able to scale to thousands of players. At the moment it will scale to about 20 players, but I'm going to rewrite that and increase the scalability. And this is the same as the notification pattern we would use in the Internet of Things for connected devices. Also the same type of notification, you know, if you're getting these toast messages popping up in your mobile device, it's the same thing. We want to alert somebody that their high score has been beaten, and so they're going to come in and play the game again. So this is the basic architecture for the game, a very high-level architecture. I'm using Windows Azure websites to actually host the website that's showing the telemetry data, showing the overall standings, showing the lap times and so on. That website is also hosting REST-based services that are supplying information to the actual game that we can make calls to. I make a lot of use of Windows Azure Storage. Instead of using just a Windows Azure SQL database to store everything, I'm using table storage to store the lap times and the driver telemetry data. The reason I do that is table storage is scalable. I can store 1 billion entities in table storage, and I can still query for those entities in 100 milliseconds if I want to retrieve particular data. SQL, Windows Azure SQL database, will not provide that much scalability. If I want to, you know, store billions and billions of entities or rows of data in SQL, I've got to think about sharding and scaling and all that stuff. I don't have to think about that with table storage. It just does that scalability for me. The driver replay data is stored in Blob Storage. I think I'm on about 50k or something like that to store the replay data for one lap. And the Windows Azure storage account can take 200 terabytes of data. So I can store millions and millions of laps of replay data just in one Windows Azure storage account. And it's very cost effective to be able to do that. The worker role that I haven't deployed this worker role. I don't have it running there at the moment, but the worker role is basically responsible for processing the telemetry data and putting that data into the storage. The telemetry data is coming in from the game into the Windows Azure Service Bus. I'm using, if you've worked with the Windows Azure Service Bus, I'm using the brokered messaging capabilities, and I'm using topics and queues. It's just basically like a queue, like Windows Azure Storage queues or MQ series or MSMQ. If you're used to a queuing-based technology, that is going to be queuing up the messages there. The reason it's queued is we could get a lot of players playing the game suddenly, and we want some kind of buffer to be able to allow messages to build up on the queue and then process those messages and get that data into the actual storage account. So as the number of players scales up, I can also scale up the number of worker roles very easily. We're working on a lab for the Global Windows Azure Bootcamp, which is going to be running next weekend, and we were testing the scalability. I think we scaled up to about 580 servers running on one particular task, 580 worker roles. We're a bit concerned because the event is going to be next Saturday, and we're expecting between 10 and 20,000 actual worker roles to be running on this particular grid compute task. But that's the kind of scalability you can get from the actual worker role capacity in Windows Azure. Usually, with my scenario, I'm running on 1 or 2 worker roles processing that data. And I'm using the relay service for in-game messaging to be able to broadcast that messaging out to the players. The website is basically hosting the actual scores, and this is reading data from table storage. So we've got 3 tracks in the game: beginner, advanced and expert, and I'm copying the Formula 1 points system. So I'm currently in first place. I've got first place across all laps, so I get 25 points for each lap, and that gives me 75 points. And you can see a couple of other students that were on one of my courses that have also been playing the game, Lucas and Andreas, and that scoreboard is kept up live as people are playing the game. So what I wanted really to think about when you're actually building these scenarios is it's not about a driving game. The driving game is fun. This is kind of what gets people interested. This is why people will come to a user group meeting to listen about it. But there's really serious points about using this architecture. This architecture would work in an Internet of Things scenario. So take away the driving game and go to talk to a taxi company, and these are going to be taxis that are going to be driving around picking people up. Harvesting the telemetry data from the taxis, being able to tell whereabouts the taxi is in town. being able to do fraud detection. Is all of the actual miles that were driven by the taxi been reported in the actual billing system? Being able to monitor the engine. Do we need to bring in a taxi for maintenance because the oil pressure is too low or the water temperature is too high? And being able to do that before the actual taxi starts failing. We're talking to a company, a taxi company, through our organisation, and they had a telemetry system in their cars that consisted of the cars having a removable hard drive under the driver's seat. And when they wanted to harvest this telemetry data, I think they had 200 or 300 of these removable hard drives that they had to copy the data from into their actual line of business systems to be able to analyse that data. That's not very practical. It would be so much better to do this through a wireless network, through a 3G network, and just basically send the data out there. And put a device that you can purchase for 20 or 30 or 50 euros in the car that can just basically send that data, harvest that data and send that data. And that technology is available for us now if we want to start leveraging it. Having the actual control and the interface on this basically brings in a lot of scenarios with security. When you're thinking about the security of mobile apps, for example, the worst thing that can happen in many scenarios is data can get compromised, or maybe a credit card information can get stolen. We kind of think that's a real complete disaster. But think about being able to take control of somebody's house, being able to take control of industrial machinery. And all of this home automation thing, it's not just about, you can turn somebody's light on and off, or you can turn somebody's cooker on and off. If you turn somebody's cooker on and off 50 times a second, that cooker is going to break. And if you can do that and have these attacks that are going to be sort of working against damaging devices, you can do a lot of damage. So we do need to think about security, and the reason for using a platform like Windows Azure is many of the Windows Azure services have very, very comprehensive security built into them. So we can leverage the security that we've already got in this platform, in these services, when we're developing our applications. So a bit about the actual architecture, digging a bit deeper into how the game is working. Lap time and storing the data and providing the scoring in there. As you drive around the driving game, messages are placed onto the Windows Azure service bus, and that's basically going to result in data being processed by the worker roles and put into table storage. And the information there is going to be displayed on those actual websites. So I'll see if I can give a quick demo of how that's working. So if I bring up the actual game itself, this is basically the back end for the game. I'm not going to dig into the code too much on this, but I will provide some resources where you can get a bit more of an access on how this is working. So just check that I'm plugged into the network and press F5 on this machine here. So what I've got running here is a console application, which is basically simulating the worker role. If the worker role is running, it's just out there in Windows Azure and it's just processing stuff, and we can't really see what it is processing there. So being able to see the actual worker role is useful in that perspective there. I kind of should have another app going. So, oh yeah, there it is, the actual driver tracker. So I'll just F5 again because it does take a while for the actual driver tracker thing to pop up. So there's the worker role, and after a while we should see the driver tracker application popping up. Now, I normally run this on the same PC, but just to show that it is an actual connected device, I will actually run on one of these PCs here, where I've got the actual game set up, so you can actually see that it is actually running across the network there. So the other application I've got running here is the driver tracker. If you watch Formula 1, you'll also always see that the team people are always sat in that little booth by the pit lane, and they're basically watching these things like the driver trackers. If you go to various websites, you can actually watch the tracker for the Formula 1 races, which will show the position of the car. I'll just tilt this around so I can actually see what's going on here, and I'll basically go in and start playing the game. If I go in start race, and I'll drop in Alan in... I'll put Alan in Finland as the actual driver name there. And I will actually show you the visuals of the game. You may be able to see it if you sat fairly near the front. So I have sort of reskinned the car with the Windows Azure logo, just for fun. And I'll just basically take the beginner track and start driving around the lap. So a couple of things I have built into the game. I have put in a DRS system, a drag reduction system, and a kinetic energy recovery system, or KERS. And that sort of allows us to analyse a bit more about the telemetry data and see what's going on. So what you see is you can see on the console application they're actually getting messages coming in the game. You can also see on the driver tracker, hopefully, that we've got my driver name actually driving around the track and competing against the other cars. I'm doing this at the same time as I'm talking, so I'm not doing too well at the moment. There's a lot of ghost cars ahead of me. But I will, it's a 60-second lap, so I'll just drive to the end of the lap. And when the lap is completed, the information will be harvested and aggregated and pushed into the website. And we should be able to go to the website for the game and actually see the information for this particular lap. This says I'm currently in 12th position, so I haven't really been concentrating too much on this particular lap. I've just got a couple of corners to go. I did actually also rewrite the physics engine for this game. If you've ever looked at the code for the XNA Racer, the physics isn't too great, so I have rewritten it and put in gravity and all of the centrifugal force and tyre slip and all this type of stuff. So it is working with a new physics engine. I'll see if I can demo a bit of that in the actual game a bit later on. So I'm coming up to the end of the lap and across the line there. And that should result in the lap being completed. We get our messages going there. So a lot was happening there. Messages were being put onto the Windows Azure Service Bus. This application here is simulating the worker role, dequeuing those messages and putting those into a table storage. And we've also got some way of being able to actually view this live telemetry data. Telemetry data can be used in two ways, two major ways. One of them is this real-time telemetry. What is happening now? How can I react against things that are happening now? And another way it can be used is by archiving the telemetry data and being able to see, okay, what has happened in the past? What is the general trend for this data or this performance or this system over the past 2 weeks or 2 months or 2 years? Being able to actually store that data in there. So I'll just sit down and fire up a couple of applications and show you a bit about how that data is being stored. So start off with a website. And we can see that Alan in Finland has actually come up in the high score table here. So I got 15 points, and if we go into the beginner track, well, you can see that I did actually get into third place on that particular lap. I've got a lap time of 1:21.996 there, so that puts me in third place. I can actually click on this lap, and this will take me to the telemetry pages, where we can start to analyse how I have driven during this lap. What we see here is the speed graph. I'm using, I think it's the Flutter Graphing API. This is JavaScript. And the JavaScript graphing API is making a request through jQuery to the actual REST service. The REST service is returning the telemetry data for the lap, and I'm building the actual graphs based on the lap telemetry data. So this is showing the overall car speed starting at 0, and we can see how fast the actual car is at various points during the lap. On the second graph down here, we've got driver input, and this is important, looking at how the driver input correlates with the speed. The text might be a bit small if you're at the back there, but the blue one is throttle, that's the one down here. Then we've got brakes coming in yellow. We've got the DRS system, this is when I was using the DRS, is coming up in red. We've got the KERS system coming up in green. And then we've got the KERS battery coming up in purple. So you can see here that when I was using the brakes, the KERS battery was charging up, and then I could use the power in that KERS battery to actually accelerate the car around the lap. Now, what I really need to add to this is superimposing the telemetry data so you can compare your lap time with somebody else's lap time. That's what they're constantly doing in Formula 1. And I also wanted to get this to look as close as I could get it to the actual real world telemetry data, looking on this slide here. So you can see this is fairly similar in that they've got the various driver inputs here. You can see the gear selection, you can see the speeds, and you can see the speed difference between two cars appearing in that top plot. It's comparing Lewis Hamilton with Jenson Button when they were both driving from the McLaren team last year. And I think the point that Lewis was making was that his car was slower than Jenson's on certain straight sections because of some settings difference that they had between the two cars. So that's basically how they're using that data. My scenario in the driving game is, it would be really good to actually, your friend beats you, keeps beating you in the driving game. Why does your friend keep beating you? Is he, using the brakes at certain points? Is he using the acceleration? When is he using his curves, when he's using his throttle. All that type of stuff, you can actually go in and look at that type of information in there. So how does the storage layer work for this? So I'm actually using Windows Azure Table Storage as the storage layer for this data. So let's go in and take a look at the actual storage account that I'm using for this. And this tool I'm using is a free tool available on Coplex, which is the Azure Storage Explorer. So going into Red Dog Test, this is a Windows Azure storage account that I've got hosted in North Europe, I think, which is the data center in Dublin. And in the tables section, you can see that it's really a test account. I've got all kinds of tables looking at what's going on in the actual driving game. And we can look at something like the test 02 lap times. This is showing the actual high scores for the various drivers during the actual lap times. So a couple of things about Windows Azure Table Storage. It does provide massive scalability. It is very, very cost effective. It does provide a really great way of being able to actually store and you know, basically store that data. However, we do have a couple of limitations. It is really hard to do, or it's not possible to do server-side queries such as select the average lap time from all of the times where the driver name is equal to Alan. We get so used to doing that in a SQL database that when that functionality is taken away from us, it does start to get challenging. So storing the data in table storage really needs to be stored and partitioned and ordered in the same way that we're going to be querying the data. I want to see the top lap times appearing on the actual website when I go to view those top lap times. So the data within storage needs to be organized in that particular way. So I think there's a zoom feature here. So looking at the actual lap times, you can see the actual lap time in milliseconds for the fastest time is 71859. So, that's 1 minute 10.851 seconds, and these actual lap times in milliseconds are increasing as we go down the table. Now we have this property here which is called the row key, and the way that I've specified in the row key, I've got 0071851. So I'm zero padding the lap time in milliseconds so that the data is ordered by the row key in the order that I want the data to appear on the actual website. So when we're working with table storage, that's one of the techniques that we can actually use there. I'm also partitioning the data. You can see partition key track 0, and if I want to query data based on partition key, I can go partition key EQ track 1. And here I'm pulling back the lap time data for track 1, which is the middle track there. And again, you can see that we've got these various values in the row key, 117012, and we've actually got the lap time there of 117012 milliseconds. Another thing about table storage is that we're not storing rows and columns here. We're storing entities and properties. So if I cancel the zoom on here, you can see that the lap times for track 0 have 8 sectors in them, and you can see the lap times for track 1. This is a longer track, and it has more sectors in this particular track. You can see there's more properties on that entity. Now in SQL, you've got to think about building a table and then adding columns to that table. You don't need to think about that in table storage. The entities have properties. The entities can have up to 253 properties per entity, not counting the partition key and the row key. And it doesn't matter what properties the entities have. All of the entities can have different properties if you so wish. So for storing something dynamically where it's different laps with different numbers of sectors in that table, table storage is cool. I can build a new track that has more sectors than the previous tracks, and I don't need to add columns to the table. I just need to add properties to the entity, and the entities are persisted in table storage, and everything works. So it's a great way of being able to store that data. Storing the telemetry data, if I go into telemetry data 0 and query this, quite a slow network here. It's loading up 2,000 telemetry entities. The query times are typically, maybe 50 or 100 milliseconds on this query when I'm running at home. That took several seconds, but that's because of the network speed here, not because of table storage. So Looking in at the actual telemetry data table, here I'm actually grouping the data together or partitioning the data based on the actual lap ID. Every lap ID will have a GUID, it's unique, so all of the data for that particular lap is going to be aggregated together in that particular partition. The Roki, this time, how the data is sorted, this is the number of milliseconds that we are into the actual lap. So you can see when the first telemetry sample was taken at 7 milliseconds into the game, and then 215 milliseconds, 321, 427. We're sampling the data about 10 times a second. And this is the stuff that I'm storing, acceleration, the brake percentage, the car type, the damage, the position of the car, distance above ground if you're doing a jump, downforce, drag engine force, and all this type of stuff. And I'm really only graphing just a small selection of the telemetry data that I'm sampling there in the actual game. Just basically putting a bit more stuff up on the graphs. And I really want to dig into this and put more detailed information out onto the actual page so people can get a better idea of how this is affecting the driving. So I've really sort of talked a bit about how the lap timing and the scoring works, a bit about how the telemetry processing works. I'll also talk about some of the ways that we can analyse this data. You can see that I've got the data running from the website. I'm also sending out some real-time information to a driver tracker. And as we build up that telemetry data, we can then do the actual analysis on this. So I haven't got this application fully working, but this application here, I'll see if I can actually zoom in on this and show you how that works. This is basically a lap analysis application which will read the telemetry data for a number of laps and then be able to actually do analysis on this. And I've just really started on that, but basically it's showing a sort of a greener colour where the car is going fast. You can see there's a loop there where the car is going quite fast around the loop. Around this corner, it's a bit slower. You can see on the corners there's basically, it's red where the car speed is lower. I've also added red dots to the actual lap, so you can see where people are crashing. Every time a red dot is appearing, that's a crash. So that allows us to analyse a large amount of telemetry data and say, okay, where's the fastest point on the track? Where's the most dangerous point on the track? Where are the most number of accidents happening there? And you can plug in really advanced data analysis tools to be able to do this type of thing. We have Hadoop technologies running in Windows Azure now, so you can spin up a Hadoop cluster and run analysis on millions and millions of laps if you want to do that. And that's what the Formula One teams are doing with their types of data analysis, to be able to figure out sort of why their car is going 200 milliseconds a lap slower than their competitor's car. The replay data in the ghost cars. There's a couple of patterns for storing telemetry data. One way that you can store the telemetry data is by sending a data stream. So this is, for example, if you're monitoring a taxi and the taxi is driving around town, picking up fares and dropping off fares. It's going to be a stream of data. You may choose to sample it every second or every 10 seconds or every minute, depending on sort of how finely you need the control on that data. Telemetry data streams, typically, they could have a beginning and an end, but it could be just monitoring stuff like temperature, where there's no sort of a definite beginning and end. Another way of storing telemetry data is just to build up all of the actual telemetry data and send it in a binary blob, or just one chunk of telemetry data that will cover the whole item. So an example of that would be, with a taxi company, would be a trip. You pick up somebody, you drive a certain number of miles, you drop somebody off, and then that actual transaction or that job or that entity or whatever you call it is finished. And you can send all of the data for that particular fare or that particular trip up to the actual system in one blob. Now, I really wanted to have both implementations in this driving game. I'm already storing the telemetry data, so I could build the ghost cars from the telemetry data that's stored in those tables. But I decided to do it slightly differently and actually have another pattern where I'm actually storing or blobbing the actual replay data into one actual sort of packet of data and storing that in Blob Storage. This was very easy to implement. The driving game already had a ghost car feature in, so when you completed a lap, if your lap was the fastest lap, it would save the actual data down onto a file on your local machine. So I just modified it and says, well, don't save it as a file on the local machine, save it into a blob in Blob Storage. changed a few lines of code. And then, instead of just displaying the ghost car for the player on that particular machine, go to the high score table, call the REST service, get the list of high scores, and then go and download the ghost cars for all of those actual players, and actually have those on the driving game. I'm still testing this. I've got a pretty powerful laptop that I got through work, which is sort of a big sort of 17-inch Dell machine with a lot of horsepower. I had that running 200 ghost cars, fine. When I tried to run 2,000 ghost cars, it was running slowly. So it might be fun, just to see how many ghost cars we can run. I also run the ghost cars around the other tracks. So sometimes you'll be, I've got sections where the one track will jump over another track. So you'll be driving along the track and you'll see cars flying above you and stuff like that, and flying off into the distance if they miss a particular corner. So I wanted to put some fun stuff in like that. So we can see how the actual ghost cars are stored. They are stored in Blob Storage, each on the completion of each lap. I mentioned that Blob Storage, I can store 200 terabytes of these ghost cars. The cost of storage is about 12 US cents per gigabyte per month. So about $120 per gigabyte per month. That is about 60, 70, 80 euros per terabyte per month. Sorry, to actually store that data there. So I can store a lot of data very cheaply, very inexpensively. So for building these large games, you look at these games that do become really popular, like Flappy Bird. If you start making a lot of money off the game, you should hopefully have a business model that allows you to store all of the actual telemetry data for your game in the cloud. So you can store your high scores, you can store your replays, because it's just so inexpensive to actually store that data. Also, the scalability is cool. You can create a Windows Azure storage account and just store a bit of data on it. I ran a course with some students at a high school in Sweden who are learning about cloud computing, and they were really concerned because, the high school students, about how much is this going to cost? How much is it going to cost to have my Azure account? This scares me. I don't know about this. So I basically created storage accounts for them. They went through a few labs. I think at the end of the course, I says, okay, it's currently costing 0.02 Swedish krona for the actual labs that you've been doing on Windows Azure Storage for the past 3 weeks. It's so inexpensive in small-scale scenarios, but then you've got that capacity where you can scale up to 200 terabytes per storage account. And you can have multiple storage accounts. Great way to be able to actually have that scalable data. In-game messaging. I'm currently using the actual relay service in the Windows Azure Service Bus. So when a lap is completed, it basically sends out data, and you will basically see that being displayed on other devices who've got the game running. I'm not going to talk for too much about that because this isn't really scalable. So there is a limit, a hard limit on having, I think it is 20 actual clients connected in this scenario. So for running a workshop at a conference, that's perfect. For running an online game with thousands of players, it's not going to cut it. But what I'm basically doing is I'm sending the data into the worker roles. When a lap is completed, it calls this relay service, and it will basically send out a broadcast message to broadcast information onto the actual lap times. There are better ways to do this in Windows Azure. There is Windows Azure Mobile Services, which can broadcast messages to Windows phones, to iPhones, and to Android. It supports all three of these messaging patterns. And I think with the current pricing, it costs something like $1 US to broadcast a message to 1 million devices. It's so inexpensive to use that capacity. So a bit about before I go into a final demo, I'll talk a bit about this scenario and a bit about how I'm using Windows Azure Storage. I haven't really had time to dig into the code or show you how I've implemented that or how I've actually written the code and actually run through that. So if you do have a Pluralsight subscription, the Windows Azure Storage in-depth course that I've done will basically run through the implementation in a much better way. I don't cover the service bus too much here, but I do explain exactly how and why I'm using Windows Azure Storage, and the racing game scenario is part on that course. Also, I have put together a Windows Azure racing game workshop. I'm running this at a few conferences, so I'm going to be running it at NDC in Norway. I'm going to be running it at DevSum in Stockholm. Also, being able to run this locally in Finland. We do have a booking there. I do have details on this booking if you want to come in and basically sit that workshop. It's really aimed at learning Windows Azure. So I've talked about it. Don't say to your boss, I want to go away and play games for a day. Go and say, I want to learn about telemetry, I want to learn about Windows Azure, I want to learn about scalable storage. So if you want to make that booking through Tieturi, then please come and see me. I'll see one of the actual representatives there. I will be around for the next. I was originally planning on being here till 3 o'clock. Till 4 o'clock. So I will be around for a while. I've got 2 actual PCs running the game. So if you do want to come down and play it sort of on the Xbox controllers and see how it works and see what's going on the back end, please feel free to do so. And thanks very much. I really appreciate the invitation to come over here and speak this evening. And thank you very much for that. And I will be around for questions if you do have any. Thank you.